Okay, so battery testing, we talked about this yesterday. And just as a refresher, what is the primary factor used to determine the amount of load used to test a battery using a carbon pile tester?
Number three.
Number three, the cold cranking amps. Absolutely. Because keep in mind, we're testing the battery. So even if I put a battery that's twice as good as what I need in my car, when we're testing the battery, we're still testing the battery. So the batteries either have to be good or bad on its own, not good enough to start the car. So other battery tests we have is a voltage leak test, a static voltage test, a parasitic load test, and a hydrometer test. So I'm going to run through these briefly. First one is the battery leakage test. And this is where we are actually checking to see if the battery is what's called self-discharging. So batteries that are dirty, batteries that have acid on the outside of them, that acid on the case of the battery can actually make a connection between the positive and negative posts, or between the positive post and ground, causing the battery to discharge.
I tested already.
So I don't know if anyone has ever had heard you should charge battery on the ground. Anyone ever heard that?
Yes.
Okay. That used to be true. So I've also heard people say, well, you can't put batteries on the ground because they'll discharge. Hello?
Hello? You're not.
My God.
All right, we're going to mute you.
Please mute.
Yes. So it used to be, if you put a battery on the ground, it would go bad. And what I can tell you is modern batteries spend a lot of time on the ground. And when you think about it, the battery tray in a car is made out of metal. So if concrete makes a good enough connection for the battery to go bad, wouldn't the metal make a good enough connection? And what if the battery goes bad, if it's on ground, what happens if I'm in the Salton Sea and I'm below sea level? Does that mean it's bad all the time? So we need to think about where this comes from. And where it comes from was in the old days, before we had maintenance-free batteries, batteries normally had acid on the outside of the battery case. So when you put it on concrete, there would be enough moisture going across between the concrete and the battery to create an electrical connection between the positive and negative post, or between the positive post and ground, causing the battery to discharge. So that's where that comes from. So that urban legend has a place in fact. It's just 40 years plus out of date. It's not an issue today. It is an issue if we see a battery that's dirty or has a lot of corrosion on it. That's something that should be cleaned, because that can cause a battery to lose its charge on its own. But there is no problem putting a modern, clean, sealed battery on the ground and charging it, letting it sit there while you're working on a car. Let it sit there for 2 months or 3 months. It's not going to hurt it, or 6 months. The last spare battery I had in my shop was on the ground for a couple years, and it still held a charge. And that was after we pulled it out of a customer's vehicle because they didn't want it. So it was a used battery, and it still kept a charge for a couple of years on the ground. And I charge it every 6 months or so. So, kind of part of what I try to cover in here is some of the things we may have been taught by people we know, our parents or other people we know that we considered experts. And there's a reason why we didn't do things at a time. We used to put it on wood or put it on other things so that it wouldn't make that connection. That's no longer an issue. So battery voltage testing. So if all I have is a voltmeter, I can connect the positive and negative leads of the battery with the key off. And I hear some echo, so I'm going to mute everybody. There we go. And so go ahead and unmute if you have something to say. But if all I have is a voltmeter and I put measure the voltage across my battery, key off, and I have 12.6 volts or 12.5 volts, my battery's pretty charged. If I have 12.2 volts, not so much. If I have 11.8 volts, then I know it's dead. So I can at least do kind of some preliminary stuff with that. And then I could turn on the headlights or turn on the blower motor to put a slight draw on the battery and see, does the battery still keep that 12.5 volts or whatever it is I'm measuring? If I turn on the headlights and turn on the blower motor for the heater or air conditioning on a car that's not starting and my voltage jumps down to 9 volts, guess what? Your battery's dead. It doesn't have anything in it. So this is where we could use a very common tool, a voltmeter, to actually get an idea of what's going on with the battery. Now, in the old days, we used to use a hydrometer. And what we would do is we would measure the specific gravity using a hydrometer. I'll show this on the next slide to figure out what the voltage is on the battery and what the state of charge is, or SOC. Well, we don't use hydrometers anymore. I mean, a couple of reasons. A lot of batteries are sealed. The other thing is I'm probably going to do more damage to the battery testing it than I do not. The other is, even if I find one cell that's low, I don't have any battery acid to put in it. So what am I going to do? I've done a lot of work. I've potentially damaged the battery, and I've actually seen that happen very recently. And even if I find one that's low, I don't have any acid to put in it, and I can't buy any. So why would I do a test that I can't correct for, and I can't do that? So what I can do is I can take this top number at 0 amps, and I can see, well, based on the voltage reading I took on the last slide, just using a DVOM across the battery, I can figure out what its state of charge is just by looking at the voltage. And so this is kind of a neat trick. So that way, now I'm using what we learned, 50 years ago doing specific gravity tests and understanding how it relates to voltage. Well, now I can just measure the voltage and understand how it relates back to specific gravity. Just like I can write multiply to get something that I can use division to prove I did the multiplication correctly. I mean, so I can go back and forth. Or just like when we were using Ohm's law, we can use, different parts of the formula to verify we did the other part correctly. So this is useful, and that's why I have the slide here, is because this 0 amps or no load voltage is a good rule of thumb to know the condition of my battery. So you can see if you're trying to get a car to start and you only have 12.2 volts, the layperson says, well, my battery's charged because it has over 12 volts. So I must need a starter because my starter's not working, or I must need a new ignition coil because it's not starting, or I must need fill in the blank. In reality, the battery, which is the heart of the system, doesn't have enough power to properly start the car or even properly perform testing. That's why we always start with the battery first. And here we are doing a state of charge test with a hydrometer. So the hydrometer is just a little float, and based on the specific gravity, the needle on it points to a scale. The issue is we suck it up, we put it out, then I move on to the next one. So we're cross-contaminating between not only this battery, but also whatever old battery or the next battery I do, as well as, like I said, I've seen, we had an instructor at the college decide to teach this, even though it's not done in industry anymore, and they destroyed 2 of our brand new batteries. So we just bought new batteries and they were junk after one class tested them. So we took a perfectly good new battery and made it a no good battery. So if I'm working on golf carts, or if I'm working on boats or something like that, where I have a lot of 6-volt batteries built into a system, then I would probably have extra acid there, and I would use a hydrometer and I would balance. And I do that about every 6 months. But for automotive batteries, we do not do this anymore. Another way of measuring the specific gravity is to use a refractometer. And we're going to use a refractometer when we do coolant. But I can also use it for measuring the specific gravity. So in this case, what I do is I take a small amount of the electrolyte solution, I put it on a lens of the refractometer, and then I hold it up to the light and look through it. And where this line is, where it separates the dark color from the light color, is where the specific gravity is that I'm measuring. And we use these for coolant, we use them for diesel exhaust fluid, we use them for a couple different things. But they will also do battery. So it's a little more accurate than the little float. But Again, like I said, unless we don't do that for automotive when it comes to batteries. So to conduct an open circuit voltage test, check your volts DC position on the digital multimeter and attach probes to the battery terminal, red to positive, black to negative, and compare the reading of those given on previous slides. So there's our static voltage test. So my question is, a battery with 12.4 volts and no loads applied, so my open circuit voltage, is it approximately what state of charge?
75%.
No.
25%.
25%.
100%.
75%.
I'd say 100.
Let's back up here.
I'd say 100.
12.4 volts is approximately 50%.
Oh, 12.4.
You see how I'm using this chart to the percentage?
Oh, okay.
So 12.4 volts means I'm at about 50%. And we also have that on the lab sheet.
Excuse me, Mr. Brian.
Yes.
It's 12.4 at 50%. It also says 12.5 is 75%. And if you look at the slide right before the one you're looking at, it talks about 12.5 being correct on the battery
Right.
voltage test. So are we saying that 75% is the correct number? That's the
There was, yes. Well, yeah, 75% is not an uncommon number, especially on a car that's been sitting. And like I said, this is just a rough thing. The real thing, because I mean, you normally don't see 12.7 volts, and I consider 12.6 volts to be 100%. And these scales will change a little bit by manufacturer. Interstate Battery has one, and it kicks it down. It separates it out a little bit more. But it's still at 12, so at 12.1 or 12 volts, you're at 25%. And maybe, instead of 12.4 being 50%, it's closer to 75. But it kind of gives you an idea of what's going on. It drops off very, very quickly. So the difference between a fully charged battery and a partially discharged battery is not very much. A lot of times people think that, well, if it's got 6 volts, it's halfway charged. No, if it's got 6 volts, it's dead because of how the voltage is created. So it's a real fine line. The battery doesn't cycle very much between fully charged and discharged on a normal 12-volt battery. The voltage doesn't move that much. And we see that with hybrid batteries also.
So what we're saying is 1/10 of a volt equals 25% of a battery's charge.
Of the surface charge, yes. And that's what this chart's saying. This chart's from GW, which was the book publisher we previously used. And that's why I've used it, because it was consistent with the book. I may switch over to the one that Interstate Battery has, which I think it rounds the numbers just, maybe 1 point on each of them. It's real close. The real concept I want here is that if you have 12 volts and a 12-volt battery, you really don't have a usable battery. So, and if you notice, the chart on the lab might be rounded a hair different than this also. So depending on the source, and you can look this up on the internet, depending on the source, you are going to see this move up and down 1 or 2 decimal points, but they're all between that 12 and 12.6. So we are dropping off really quickly, Rob.
But you can start a car with a 9.6 volts.
At 9.6 volts under load,
No
the
load.
minimum voltage the car will start. But again, that's pulling 200 amps out of the battery. So under load, I can still start the car, but that's actually after I've already used all the power starting at that 12.5 or 12.6.
So I guess what I'm reacting to is if you ask about 12.4, I could argue that it's either 75, 50, or 100 really.
Well, it's not 100. It's
Well, based on the
100.
previous slide, it might be.
Well, 12.4 is never going to be 100. 12.5, you could argue that, hey, I'm basically fully charged or very close to it. That's, 80%, 90%, whatever. The chart in the lab sheet, I think, is consistent with this, but it does drop off really quickly on each 1/10 of a volt. Because again, keep in mind, this is with nothing connected to the battery. This is just what does it have with no loads applied.
Mm.
So at 12.6 volts or 12.5 volts, I can put loads on the car and I'm still going to probably maintain some voltage. If I'm at 12.4 volts and I turn the headlights on, I might quickly be down at 10 volts because it doesn't have the capacity anymore. So the voltage is really an indication of capacity more than actually what the voltage itself means, if that makes sense, Rob.
Pretty much with this battery, you have to put a little bit of load on it to see how strong the battery is. Otherwise, it's pretty much like a ghost voltage.
Exactly. Yeah. It's more like voltage potential, not what we can use. And that's why on that, open circuit voltage test, there's such a small difference in voltage between the different states of charge.
Yeah, I seen that before. The battery seems like, at 12.4, just, turn on the light and boom, it just drops really quick to 7 volts. Yeah, it's just like a ghost voltage without load.
Exactly. Sometimes people call it a surface voltage. Sometimes a battery tester will say, hey, there's too much surface voltage because you're over that 12.7. Maybe you're at 13 volt surface voltage. So it has you turn the lights on to get rid of that surface voltage and get down to what the battery actually has. But the difference between a fully charged battery and a discharged battery is a pretty small number. Whether it's a hybrid battery or whether it is a 12 volt car battery. So it is, it stays high for a long time and then it just quickly drops. And I think that's why a lot of people really get confused trying to do starting system diagnosis or charging system diagnosis because they're trying to get a car to start. And the battery, when they take it to the auto parts store, has 12.4 volts or 12.2 volts. And in your mind, it thinks, man, there's plenty there. That's almost 12.6. It should be starting the car, no problem. But in reality, it's lost a lot of its capacity, or it's lost 50% of its capacity. So that's really where it affects it. So it's not that the 12.4 is 50% of 12.6. It's the amount of capacity or energy available in the battery.
So I guess what I'm
Sir,
reacting to is that where we said on the previous slide that it should be 12.5, and now we're saying that 12.5 is 75%. So we're saying it should be, this reading should represent 75% of a good battery.
Well, let's back up a second here. Okay, so what I did is we turned on the headlights or blower motor, and then the voltmeter should read 12.5. So if I go now, because now I'm no longer in a no load situation, right? I put a load on the battery. So if I look at 5 amps is 12.5. 15 amps, I should have a minimum of 12.3. So because we turned the headlights on, that 12.5 would definitely be a good number.
How much voltage is it at the start?
Without the load. Okay, thank you.
Yeah, you see, because I think in our discussion, I think we missed the fact that we turned the headlights on and then measured the 12.5.
Okay, so we're reading with the load at 12.5 and
Right. And without a load, I'm going to be at 12.6, 12.7.
okay, thank you.
You bet.
So when you start a car, how much voltage?
Well, how much voltage do I
Is used.
need when I start, or how much do I have while I'm cranking?
No, as you're cranking.
It depends on the vehicle. Normally we see somewhere between in the 11s down to about mid 10s. If I get, the minimum acceptable voltage has always been considered 9.6 for most vehicles, because below 9.6, computers don't work. And even if I go on the Wayback Machine below 9.6, I don't make a hot enough spark with my ignition system. So that's why that's always been the minimum cranking voltage, because other things don't work and the car doesn't start. But in reality, a modern vehicle, I would expect it to be somewhere between 10.5 and 11.5 volts cranking, maybe even higher. Because some of the starters we have on modern vehicles are very, very small compared to what we used back, on big V8s in the early 70s.
Sir, I have a
Good
question.
Yeah.
On our lab sheet, I don't know if I hear it wrong, but you said the CCA is 303 and the volt is 12.17. And the recommendation is charge and retest. And
Correct.
I thought it's 12.6 volts will be 100%. And you read 12.17 in the recommendation charge and retest.
Right, yeah, so we had 12.17, right, or 12.2 volts?
Yes.
Right, so the recommendation is charge and retest because it was a before charging test. If I had charged the battery and I still had 12.2 volts, then we'd say the battery's bad. But
Oh, okay.
because we haven't charged it, because maybe someone left the lights on, maybe the battery's been sitting for 7 months. So that's why the tester says charge and retest, because it's saying, you know what, it didn't test good now, but you started with so low voltage, we want to charge it all the way up and retest it.
Oh, okay.
Well, great questions.
Thank you, sir.
You bet. Great questions.
So if you get like 12 volts and it's still between 12.50, would it be a high? 12.50 or 13.50 on the
What, the
value?
battery?
Yeah.
The battery shouldn't really be above 12.6 volts. Occasionally, you'll see a battery higher than that right after you shut the car off. And if you turn the headlights on for about 10 seconds, it'll get rid of what's called a surface charge, and it'll bring it into the normal range.
Because I've seen a lot of cars, they have like 13.50. After
Not at the battery, maybe with the engine running, that would be the charging system, but not the battery.
Yes.
No, it's battery after you turned it off because it was having a high charge rate. For some reason.
Right. So that we call that, like I said, that's a surface voltage, and that'll either dissipate on its own or you turn the headlights on for about 10 seconds and it goes away.
Oh, that one, it stated
So
like
think
that.
of it kind of like
No,
it
stated-
won't stay there like that.
No, I seen it stated the next day. It still had it the surface charge of 13.50. It didn't go down. What would the problem be?
Well,
If
the
it's
problem, well, you know, I've only looked at a couple thousand batteries and I've never seen one do that. But the problem would be the battery was overcharged.
Yeah, how would we fix that normally if it's overcharged?
Well, you put a load on it. You turn the headlights on or you use a load. And you need to look at what's charging the battery and why did it overcharge.
Could it be the alternator sometimes?
Could be.
Right, because I've seen some cars with higher alternator outputs, and then it kept the battery charged at 13.50 on some.
Well, the alternator is going to charge normally between 13.5 and 14.5, but when you shut the car off, the battery is going to drop back down to the capacity of the battery.
Yeah, the battery capacity was 1,000 cooking amps. It was an upgraded one.
Yeah.
Have you seen those ones with the screw-on type?
Yeah.
It's like a dry cell.
Well, it's not a dry cell. We talked about that yesterday.
Oh, I mean the glass mat cells.
Yeah. It could be an AGM.
Would those ones hold up high cranking amps?
They can hold high cranking amps. They can also hold the surface charge longer because they're not supposed to be charged at 13.5 volts. So the reason why an AGM battery might be holding a higher surface charge is because it's been overcharged. So we talked about yesterday why we don't use AGM batteries in cars with normal charging systems. And that's one of the reasons why.
Okay. Yeah, it's because it was a second car.
Yeah.
My friend had it sitting.
Current draw present when engine and electrical.
So one of the issues we have is that batteries go dead sometimes. And a lot of times people blame the charging system or the alternator. Sometimes it's just a bad battery. Either it's dirty or it's gotten old. Or sometimes we have what's called a parasitic load. So a parasitic load is basically, like it sounds, a parasite. A parasite, robs or steals from its host. So in the case of batteries, all batteries on modern vehicles have some parasitic loads. And that might be your vehicle's alarm, some different computers on it. Think about it when you come up to the car and you push your button to unlock the door, someone has to be awake, right? So whoever's awake is using battery power to stay awake.
Yeah,
So
my
over time, what's that?
my car does that, Mr. Brian. The engine is turned off. Nothing's but if you turn on the radio, it's gonna come on.
Right. So, and that's probably because of how the radio is wired, because normally you wire a radio through the ignition switch. And sometimes if it's, especially if it's an aftermarket radio, they wire it directly.
Yeah.
Is this where reserve capacity becomes important?
It is where reserve capacity becomes important, because that is why I have to have at least the reserve capacity that manufacturer recommends, because all cars have that parasitic load. So if I have a S-Class Mercedes, it's going to require a higher amp hour capacity because it has a lot more parasitic loads than my little 4-cylinder Toyota Yaris will, right? Because there's a lot more bells and whistles on that S-Class Mercedes, a lot more computers.
Yes.
So, you know, parasitic loads are what cause a car to be dead when you leave it parked for maybe 2 weeks, a month, 2 months, whatever, depending on the size of the load. So all cars have a parasitic load. And that's why we do have to match the correct battery and it has the correct reserve capacity or amp hours. However, occasionally we get an abnormal amount of load, or we have a customer complain that their car is fine if they drive it every day, but if they park it for the weekend, it was dead the following Monday, and it's happened twice. Things like that. So a parasitic load could be something that the customer left on. Maybe they left the dome light on or the map light on. I've done that, right? That's a load that's on the car when the car is shut off. Sometimes, or a driver, someone doesn't shut the door all the way. So those things have all happened. I remember when my kids were small, I went out to take them to school in the morning. The rear door of my vehicle is wide open because one of my daughters didn't shut it the night before. So, you know, amazingly enough, no one went in and took anything, but it was sitting out in front of the house with the door wide open all night.
I actually have a similar experience that that I can share. So this is prior to well, this was in the beginning of me taking the classes in 600. I came out, my car was completely dead. So I'm like, oh, it must be the battery, right? So the battery, so I went and bought a new battery and I installed the battery, drove fine. So as I was exiting the vehicle, it was nighttime at this time. I exit the vehicle, I hit my alarm, and as I was walking away, my brake lights were still illuminated. So my brake light switch, the pedal wasn't making contact with the switch, which was leaving my brake lights on all the time. So knowing that now, I could have just probably charged the battery and the battery would have probably been fine, but I purchased a brand new battery.
No, and the awesome thing about that is that's such a real story, because I've seen it happen so many times. And you got lucky that you parked the car in the dark and saw the brake lights on, because a lot of times what happens is people go through their next battery. It's new, so they charge it a couple times. Well, batteries, because they're made to shallow cycle, not deep cycle on the car, after it going dead a couple times, now it's no good. So now they go back and warranty the battery. So after they've been chasing the problem, been late to work, had all these problems over the course of a couple of weeks or a month or two, then they bring it into the shop and ask the shop to diagnose the problem. And then the shop finds that, oh, let's check for a parasitic draw. And we figure out that the brake lights are on all the time. Or being in the shop, people are walking by and someone goes, hey, do you know your brake lights are on? So, you know, you got lucky that you kind of stumbled across it, but by the same token, you were able to figure out that, hey, if the brake lights are on all the time, it's going to cause my battery to go dead. And believe it or not, a lot of people don't make that connection.
Since this happens so often, I have two questions. A, since I know the amp hours of the battery, can I check for the amp draw when everything's off? And then I'll know how many hours that car can sit there without being started. And B, can you go through your procedure for checking for parasitic draw and because it happens so often, and narrowing it down to something that we can repair.
Yes and yes. So most manufacturers publish a number that is the maximum amount of parasitic draw allowed on the vehicle. And so that's in our repair information. If the manufacturer doesn't publish a number, we usually use 25 milliamps. So if I have 25 milliamps or less, I don't have a problem. If it's between 25 and 50, I probably need to look what kind of vehicle I'm working on. Some newer Fords are 48 is their spec, things like that. If it's over 50, it's a good sign I probably have a problem, but I still need to look up the manufacturer because some Mercedes are allowed as much as 70 milliamps. But we use 25 as that magic number. If it's less than 25 milliamps, I can take my car to the airport, let it park for 2 weeks and pick it up, and I'm not going to have a problem. And I know that without doing all the hard math. If I have more than 25 milliamps, I either need to have a spec telling me it's okay, or I need to diagnose it. So that's the number we use. So if I'm going to test for that, I'm going to check for abnormal current draw. So abnormal is anything above what the manufacturer says is okay. And I need to wait a little while when I do this test. So what I'm going to do is I'm going to make my amp meter connection. And this is really the only test I use the internal amp meter for. I don't use an inductive clamp because it's not accurate enough. I'm going to close all the doors, all the windows, turn off all electrical before I make my meter connections. Make sure that if there's an underhood light bulb, I'm going to make sure it's off. And then I'm going to wait, because on a modern vehicle, computers can take over an hour to go to sleep. And a computer is going to use 1 to 200 milliamps. So I need to wait and wait and wait and come back and check it in a half hour or an hour and see what that final number is on a modern vehicle. If I'm working on something from the 90s, I might only need to wait 2 minutes for the computer to go to sleep. It didn't take them long. But I need to be patient on that. And I'm going to read the amp meter reading compared to specifications. And so I need to hook the amp meter in series. So in this case, they went on the negative battery in this picture. I normally go on the positive, but you can go on either one. It doesn't matter. And then what I'm going to do, if my number's too high after everyone should have gone to sleep, I'm going to start taking out fuses that are marked hot all the time. Because the fuses that only have power when the key is on, I don't need to test because the key is out of the ignition. I need to concentrate on the fuses that are hot all the time. If I pull out all the fuses that are hot all the time and I still have a draw, then I need to disconnect the alternator because I might have an alternator problem, or I need to look at the wiring schematic and see what other paths I have for current to flow after I've taken that out. Maybe there's some fusible links. Maybe there's some other stuff that might need to be disconnected. But normally, once we start taking fuses out, and when we take a fuse out, when it's the one with the draw, we see that number drop down to either 0 or to an acceptable number. Now I know what circuit is bad. So what I'll do is I'll reattach the battery, take my meter over and put it in this circuit in place of the fuse. And then all I need to do is diagnose that circuit. So it's kind of like starting at the main branch of a tree and they get it on the big limb and then smaller limb and smaller limb. So we're going to use our wiring schematic as soon as we figure out what this fuse goes to figure out, what do I want to disconnect next? Is it easier to disconnect the connector, or do I need to disconnect the radio, or what is going to be easiest for me to disconnect to see where's the next place that's easy to get to? I can unplug something to see if the problem goes away.
Mr. Perrin?
Yeah.
Okay, you said a fuse that's hot all the time.
Yes.
What do you, like temperature hot? I don't understand.
Okay. This goes back to when we were looking at schematics. And if a fuse is hot all the time, that means it has unswitched battery power.
Oh, okay.
And one of the things it said at the top of the schematic was hot always, or hot always, I think it said. So no, thank you for asking that. I'm sure you're not the only person that had the question. So when we talk about something being hot all the time, that means it has battery power all the time. It is not a switch. Where other fuses for things like my radio have to go through the ignition switch. So that fuse is not hot all the time. It's only hot key on. Does that make sense, Connie?
Yes, sir. Thank you.
You bet. Great questions this morning.
Mr. Brian,
Yeah.
like on the fuse box, instead of pulling the fuses, and I use an extra ammeter to check that fuse without moving it. That way I don't disturb the circuit.
No, because you remember amp meters have to be hooked in series. If I hook the amp meter in parallel across the fuse, it won't give me an accurate reading. What we can do is use a voltmeter across the fuse, knowing that fuses all have resistance. So if I have current flow, I would see a voltage difference between the two sides of the fuse. And there's actually a chart on the Power Probe website that shows you what kind of fuse, the size of that kind of fuse, whether it's a regular standard fuse or a mini fuse or so on, and what the voltmeter reading means in amps. So there's actually conversion charts on the Power Probe website you can look up. They used to be on Lifelike fuses. They got rid of them before, and I understand they're on Power Probe right now. And Chrysler, about 10 years ago, that's how they actually have their technicians diagnosing parasitic draws going to computers and things, because they don't want to disturb the circuit. The issue I have is that that's great if I have a big parasitic draw, an amp, right? Or half an amp, a big draw, 500 milliamps. Most of the draws I'm trying to find, I'm looking for 30 to 50 milliamps when the customer brings the car in, and a voltage drop test on the fuse won't show you that. And that's why I take the fuses out.
It's not gonna like split, like you have, let's say, like 50 milliamps, and you just like plug the other two, connectors from a second ammeter. It's not gonna split like 25, no.
Yeah, the problem is the inductive clamps. They're normally a 20 or 60 amp clamp, are not accurate at that 20 milliamps. They do sell a milliamp clamp that you could do this whole thing with a inductive clamp, but those clamps are still about $500. The price on them hasn't come down, so I haven't bought one. So I still do it the way I always have. The other thing I do that's a little different is here we're using a digital multimeter. What I use is a graphing multimeter or a scope, which allows me to see the changes in current over time. So that allows me to walk away from the vehicle for 5 minutes at a time or 10 minutes at a time. And I can come back and look at the movie that was taken while I was gone to see if anyone woke up. Did anyone do anything? Did the computers go to sleep? And am I now down at the low number? So I always use my Vantage, which is a graphing multimeter and lab scope, for this test, because I don't want to be stuck here glued looking at numbers. And at the same token, I don't want to miss anything. So I like to graph it, and I'll get into graphing things more as we get into subsequent chapters. But I like to graph things because that way I don't have to look at all the time. I don't have to worry that I blinked and I missed something. I can see that happen over time.
Okay, I was just asking, yeah, because I was curious about, like, because right now with modern cars, you might end up probably waking up some modules while you pull the fuses.
Right. Absolutely. And that's why Chrysler came out with the voltage drop testing across the fuses. So you're not waking modules up. But the module is only going to wake up when you put the fuse back in. So usually what I do is I just start taking out fuses. I'll take out one, I'll take out the next one, I'll take out the next one. And I put them in line so I don't mix them up until the draw goes to zero. And once it goes to zero, then I'll start plugging back in those other fuses. And if the number goes back up, then I wait for that module to go to sleep. And I make sure that with all the other fuses in, that one fuse is the only fuse with the draw. So I don't unplug the fuse and plug it back in, because you're right, I'd be waking up a module every time. I just unplug fuse, unplug fuse, unplug fuse until I finally hit, oh, that's the fuse with the draw. I leave that fuse out. Then I start plugging other fuses back in.
So you don't do them one at a time, like pull one out, plug it back in?
No, because if it's attached to a module, that module is going to wake up. It might be 10 minutes or an hour before I get back to a reading that's stabilized that I can pull the next fuse. So since I pulled that fuse and nothing happened, I'm just going to move on and pull the next fuse. And that's why I lay them out in order where that way it's the same order as what they are in the fuse box. So if it's 7 down and 4 across in the fuse box, I'm pulling a fuse out 1, 2, 3, 4, 5, 6, 7, then 1, 2, 3, 4, 5, 6, 7, and so on. And that way it is, that way they're in order, because I don't want to mix up fuses. I don't want to leave fuses out. So sometimes you'll have 7 fuse cavities, but only 6 fuses. It comes down 4, misses 1, and then has 2. Well, I'm going to leave that blank space on where I'm laying them out on those fuses when I take them out. So I don't even check which ones are hot all the time and which ones aren't. I just start pulling them out, and because I don't want to, it takes so long to count fuses. I just pull them. I can pull them all out pretty quick. Boom, 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 boom. And look, if I'm using a wiring schematic, then I pull only the hot first. But, like I said, there's not one right or other. The big thing is not mix them up. And for me, it's quicker to pull 5 fuses or 20 fuses than it is for me to go look up and see which fuses do I really need to pull. So I kind of cast a wide net. I'm a little sloppy that way.
Mr. Ryan?
Yeah.
Sorry, one more question. So in this case, can we use a thermal camera? Do you think it will show you which one it has a little
Oh,
bit of
can we
temperature
use
or
a
no?
thermal camera? Great question. When I first bought my thermal imager, I was all excited. And I didn't have any luck at all finding parasitic draws with it. And a friend of mine, who I work with, when we came into the winter months, he decided to try it first thing in the morning. And first thing in the morning, when it's cold out like it was this morning, the thermal camera works pretty good. When it's during the day, or if the engine's hot, the thermal camera is not going to work, because the engine puts off so much heat, you're not going to see the small heat generated by the current flow through the fuse. So if you're going to use the thermal camera, because you can look at relays, fuses, everything's with it, you need to do it first thing in the morning when it's cold, before it started, before the day's warmed up, and then it seems to work okay. And the mistake I made, being dumb, is I tried it under the hood with an engine that's hot on an 80-degree day. And hard to believe it didn't work.
Oh, thank you. I was just curious, because like when it comes to diagnostic, you need to have a lot of arsenal, like
right,
a lot of different techniques to do diagnostic. Thank you.
Absolutely. And I still go with the old school with it, but if you isolate it, you do have a draw. Sometimes the thermal imager, especially on Euro cars, is real helpful for finding it, because there's so much stuff. And for those of you who aren't familiar with what I'm talking about by a thermal imager, it's handheld and has a screen on it. And based on the temperature of things, it's different colors, from a light color down to a purple. So the cool stuff's purple, and then the light stuff is almost white or yellow. And so it allows you to see, and it calibrates based on what it sees. So if the hottest thing in the picture is 80 degrees, it's going to show a big difference between something that's 80 degrees and 50 degrees. But if the hottest thing in the picture is 400 degrees, then whether it's 80 degrees or 150 degrees, it's all going to be purple, because the 400 is so hot. So it's a relative thing, and you can point around and point to different things in your picture to see the temperature. And I actually pull it out in cooling systems, and you'll see me demo it. So that's a tool that I do demo here during the class. So in order to connect an amp meter directly to measure parasitic draw, it must be connected in what way?
Series.
Series. All right. So discharge 12-volt battery causes. This is more just an FYI brain thing for you, and I have it in the PowerPoint. So a defective battery could obviously cause it to be bad. Shorts inside a cell, low electrolyte, or freezing damage. That's like saying a defective battery or bad battery. Charging system problem, poor cable connections, engine performance problem. So here's an example where a car might crank for 1 second normally, or 2 seconds, right? But if your car's having a problem starting, you got to crank it for 10 seconds every time to get it to start. The battery's not designed to do that. So that's going to cause, especially if you're doing short trips, that's going to cause the battery to go dead. An electrical problem, drawing current out of the battery with the key off. That's our parasitic draw. So these are some of the causes of discharged batteries. So what causes voltage drop? We know this, right? Because we just learned voltage drop in the last module. Voltage drop is caused by resistance, inner resistance when current flow is present. Wanted resistance in our load device, which is designed to the system, such as a light bulb or starter, and unwanted resistance is caused by damaged wiring or bad connectors. Since the entire car is a parallel circuit starting at the battery, someone mentioned that in this class, we should start there. So we're going to look for loose connection at the battery. So, and he'll talk about improper battery replacement and corroded battery cables. So a couple things here. First of all, these are do-it-yourself battery cable ends. You can buy them at any auto parts store. They're not recommended, but they will get you out of a jam and they can save you money if you can't afford to buy the whole cable or the cable's part of a harness. The issue is if I use these, it doesn't stop battery acid, if the battery leaks, from getting up into the cable and wicking down the cable. So the cable you see right here, this corrosion is from battery acid. And I actually pulled this battery cable off a car with a side post battery that was leaking, and it had battery acid dripping out of the starter. So this cable had acted like a candle wick, and the battery acid came from the battery. The battery looked nice and clean, went down the battery cable all the way into the starter and was dripping out of the starter. So the car obviously needed a new battery cable, and a new starter. And they just thought I was guessing what was wrong. But battery cables will wick battery acid. So if you have battery acid damage on a cable, it's not limited to just the end you can see. Many times it goes at least this far into the cable. And so by the time we get to a good material, there might not be enough cable left. So there's two different kinds of cable repairs that we have. And then of course you can replace the entire battery cable. And sometimes that's the most cost-effective and efficient method, but other times it's not. So we have an improper or DIY repair, which still allows battery acid and corrosion to get into the battery cable because it's not sealed. And then we have a professional battery cable end repair where we've actually crimped or soldered the battery cable end on and then used heat shrink tubing to seal it. So it's a sealed connection. So if you buy a brand new battery cable, you should not be able to see any of the cable between the battery cable end and the insulation on the battery cable. If you do, the battery cable you're buying is defective. At the factory, when they crimp that together and seal it, it's supposed to be sealed. Occasionally you pull a brand new battery cable off the shelf and you have the battery cable end here and the battery cable here, and you can actually see a millimeter of cable between the two. That's a bad cable. Don't buy that one. Give it back, explain it's defective, and tell them you want one that's put together properly. So there's some battery acid damage on that one. So in order to replace the battery cable end, the cable must be sealed. Is that true or false?
True.
True, absolutely. Because what I see happen a lot is someone will put on a battery cable end. They got plenty of battery cable. So they've cleaned it up. They put a new battery cable on, they're good to go. 6 months, a year later, it's now corroded. And not only has it corroded the cable end again, but it's corroded up the cable. And now that cable's ruined. And sometimes, like I said, these cables are just unreasonably expensive. And now the customer can't just put an end on it because there's no good cable to attach an end to. And that's why. So if you're paying money at a shop, the shop should not be doing this. If the shop's charging you money to put a battery cable end on, it should look like this when they're done. This is the correct way to do it. And think about it. If you're paying money for someone to do something, which looks better, the one on the left or the one on the right?
One on the right.
Right. I'd feel good paying about the one on the right, the one on the left, and not so much. So remember I said we're doing voltage drop testing. We want to start at the battery. So what we're doing right here is we're actually doing a voltage drop test between the battery post and the battery cable. And here we have over a 1 volt drop, which is huge. So just because it's tight doesn't mean it's electrically connected. So I can have something mechanically connected. It's tight, but it won't conduct electricity properly because it has corrosion. So, grabbing it and seeing if it's tight is a good first test. But don't assume just because something's tight, I don't care if it's a battery or any other electrical connection on the car, don't assume that because it's tight, it's good. I've had cars where I get as much as a 12-volt drop going across between the battery post and the battery cable. And believe it or not, the worst one I had is one that the customer had already put in their own battery. And they had tightened it up, but they didn't clean it. So therefore, even though it was tight, it didn't have a good electrical connection. So when we clean the battery terminal post, we actually, they make two different kinds of cleaners. One is like this. These are only a couple bucks. It has wires inside and you scrub them. The other ones are more expensive and they actually cut the lead and reform the lead. And here we see a couple different tools. We can use a wrench, or if it's so corroded, they make what's called battery pliers if the nut's all rounded off to get the nut backed off. And then they make a special puller to pull the battery cable off. And then you can clean it. And if the battery cable doesn't go down all the way, they actually make a tool for spreading it out so we can seat it back down and everything. But normally after you clean it, you're able to get it back down and tighten it up. But you want to make sure, just like we talked about yesterday, you have that taper on the battery post. We want to make sure we get to the bottom of the taper. What a lot of times people do is they put it on as far as it'll go and then tighten it up some more, where they're making the clamp smaller and smaller and it's higher and higher up on the battery post, and it makes for a bad connection. So let's jump out of 12-volt batteries and get into some high voltage batteries. I noticed on the discussion posts from this section that a lot of you are really interested in hybrid and electric vehicles, both from a performance standard and from an emission standard. So since we're talking about batteries and a battery's a battery, let's talk a little bit about hybrid batteries and some of the precautions we have for hybrid batteries, how they build hybrid batteries, as well as how we test hybrid batteries. And we test hybrid batteries very differently than we do a 12-volt battery. And so I just kind of want to touch on this a little bit as an introduction into hybrid batteries. Certainly we could go a lot deeper into that. But this is really enough. I want everyone to be safe and really understand the basics at this point of a hybrid battery and how it's going to be tested. So sometimes these are also called a battery stack or battery bank. They store chemical electrical energy for starting the initial internal combustion engine, for full electric propulsion, and in some cases provide the 12 to 15 volts DC for electrical accessories in conventional electric circuits through a DC to DC converter. So our hybrid vehicle, the lights on it, the radio, everything else still works on 12 volts. Almost all of these still have a regular 12-volt battery. Matter of fact, I'm not aware of any that don't right off. That being said, what we are able to do is subsidize power, because I can use my charging system, my motor generator on a hybrid vehicle to charge the 12-volt battery. But I can also use my high voltage battery that has 140 to 370 volts, depending on the car, to charge a 12-volt battery. And we use a DC to DC converter. So we're taking that high DC voltage and making low DC voltage. And that's what we tend to power things up with. And I can charge the 12-volt battery with that.
Is that just another transformer? It's like a step-down transformer?
Yep, you got it. It's basically just a step-down transformer.
No alternator.
There is hybrid vehicles do. Most hybrid vehicles, 99 point something percent of hybrid vehicles do not have an alternator. There is some hybrid systems that are called a belt alternator starter. I would still not define that as an alternator. And those are called a belt starter assist system, or BAS system, was GM's name for it. Those are somewhat common. They're becoming more and more common. We see them on everything from BMW, Mercedes to Chrysler. Again, they're using the term alternator, but it's really not an alternator. It's an alternator starter motor. It's a three-phase motor. The number of hybrid vehicles that use a conventional alternator are very, very small and very, very early. So we really don't have an alternator on a hybrid vehicle, just like most hybrid vehicles do not have a 12-volt starter. There are some that do, or some that did, but most of them don't.
If there's no alternator, are you relying on things like your brakes to regenerate?
Well, you're relying on the brakes to regenerate. You're also relying on the gasoline engine to regenerate or to generate power.
Transmission.
Wouldn't your gasoline engine drive the alternator in order to do regeneration? And if there's no alternator, then
Right. So what we have is a motor generator. What, and I'm going to get to it in a couple slides, and I'll show you a cutaway of a Toyota. But the advantage of a three-phase motor is that it can act as a motor and as a generator, depending on the polarity of the phases in the motor. So all we have to do, we don't have to change rotation of the motor. All I have to do is change the polarity of the phases, and I can turn a motor into a generator or a generator into a motor. And so hybrid vehicles use that motor generator, and that motor generator can be generated by the wheels going down the road when I'm using it to slow the car down. I can use it when I fire up the gasoline engine. So there's a lot of options I have for turning that generator. So every time you let your foot off the gas, I have the potential to generate electricity. If I put my foot on the brakes, I'm telling the computer I want to slow down. Now I'm going to increase the electromagnetic field on the generator, and that is going to cause it to charge at a higher rate. So we can really control the rate of the charge based on the intensity of the field. And then same with accelerating. Do I want to accelerate lightly, or do I want to make the tires slip? Well, again, based on the intensity of the field, the amount of amperage flowing through, it determines the amount of torque that the motor is going to apply. So give me a second. I got a picture of a Toyota with both motor generators, and I'll just kind of show you what I'm talking about that Toyota does. So the first thing I want to show you is safety. So these are service disconnects. Many times when I'm working on a hybrid vehicle, the manufacturer will ask me to disable the high voltage system. So the high voltage system, a couple things about it. First of all, my high voltage system, anything over 60 volts is going to be normally shown with an orange wires. And some manufacturers carry that over to their safety disconnects and put their disconnects in orange. That's why you see this bright orange. Other disconnects will have a little lock on them. So you have to really deliberately want to disconnect it. The one here on the lower left is on a Honda. This is behind the back seat. You take the back seat, rear side of the back seat off, and you got this switch, and you can't take this metal cover off unless you turn the switch to off. If it's on, it interferes and it physically won't let you take the cover off because you can't get to this nut right here. So it kind of forces you to be safe. This is Ford. This is like off a Ford Escape, and we have a lock, an unlock, and a service. So I can lock it here so that it can't, so it can be disassembled, or so that no one can accidentally do it. This is a Toyota one, you also used by several other manufacturers, and it has a little slide for positive engagement. So there's a little switch right here that tells the computer, yes, this is engaged. If I pull this back like it's partially pulled back right now, then it'll open this up and it'll set a code, and it'll prevent the computer for connecting the high voltage battery. And then once you pull this completely off, you actually take it off. And what technicians do is they'll take this off and put it on their toolbox or whatever. And the reason why they do that is we don't want someone other than ourselves, or ourselves absentmindedly, to accidentally turn the key on or accidentally do something that would cause the computer to connect the high voltage battery to the high voltage system when I'm working on or near it. So this is all for safety. That's why they call these safety disconnects or service disconnects. And that's why manufacturers tell you to disconnect them before servicing the vehicle. And even after we disconnect them, we still have to verify there's no power. So we need to wait for the capacitors to drain. And normally it takes about 10 minutes for the capacitors to drain. And then we need to use a digital multimeter to verify there's no voltage present in the high voltage system and the battery's isolated. before we work on anything. And if you notice here, the technician is wearing safety gloves. So these are special gloves, and they're made up of 3 parts. They have a cotton inner glove because your hands are going to sweat at them. And then you have a synthetic rubber electrician's glove that must be certified every 6 months. If you buy brand new ones, they're good for a year. After that, they have to be mailed in to be certified. You have to test them for leaks every time before you put them on by blowing air in them, closing it and turning up and make sure that it doesn't deflate like a balloon. And then these outer gloves are goat skin gloves to prevent you from putting holes in the electrician's gloves. So you can see it's very, very bulky to wear these gloves. Once we verified that there's no power in the system, then we can take the gloves off and work on the system, because a lot of these components are very small and you can't access them with gloves on. So we need the gloves while we're disabling the system.
Sorry, do you have pictures of the gloves?
I do, and I realize I put them in for another PowerPoint that I built, and I just realized that I had not grabbed them out of that class and stolen them for you guys. So I will do that, because I didn't put them in this PowerPoint, but I did actually build a slide on that for another class. And I meant to put that in here. So let me do that, or I'll grab it today. I'll grab the other PowerPoint and just show you that, because I know where that PowerPoint is.
Also, isn't it true to have all sets of gloves, the rubber insulation and then the abrasion resistant on while you're doing the high voltage disconnect?
It depends on the manufacturer. Some manufacturers want that, some don't. Toyota, for example, does tell you in the instructions to put on the gloves to pull the disconnect. The issue is when you look at the wiring schematic, there's no voltage at the disconnect. So I never put on gloves because there's no voltage there. Why would I wear gloves to protect me from voltage that doesn't exist? But the manufacturer, because they're so worried about you getting hurt, tell you to put gloves on. Are you following?
On the safety class also.
What's that?
Safety class.
Yeah, you're supposed to have safety glasses on all the time when you're in the shop. So that's unspoken. It's like me telling you to put pants and shoes on. Right?
Yeah, no, I got it. I was just referring because I read something I think in the previous chapter about, you know, they instructed gloves, and also like you mentioned, once you pull the disconnect, to either store it somewhere where you only have access or put it in your pocket, as you mentioned, so no one else can go and install it as you're working.
Right. And your question on the gloves on pulling the disconnect is a great one, Christopher. For example, Ford does not request you do that on their Escape. This is BMW right here, and there's actually no voltage going through this one, so they don't spec it out. So it really kind of comes like this is GM. They do not request you use gloves. Toyota does. So some manufacturers do and some don't. Manufacturers are terribly concerned that we are going to kill ourselves. And to be fair, there's enough voltage and amperage there to do that. So when in doubt, put the gloves on. I'm one of probably 1,700 people in the country that are ASE certified in hybrid and electric vehicles. So I'm very comfortable with them. So I know what I can and can't do. If I'm ever in doubt, I'm going to exercise extreme caution and safety, because I do understand the dangers involved. And and that's why I show the picture with the glove, and I explain, you know, the gloves. So I do need to get that picture in here showing the gloves.
Understood. So basically just always refer to the manufacturer specification.
Absolutely. And like I said, I'm bad. I occasionally will do something different than what the manufacturer recommends, because I have enough experience to know I don't need to do that step. You know, for example, I have an old Chilton manual, and step 1 to every task is remove the negative battery cable. Well, in reality, I don't need to do that for a lot of tasks. On a modern car, I'm going to create a lot of problems if I disconnect the negative battery cable. and I might actually damage stuff. So even though the directions kind of have that blanket thing, I have to keep in mind what I'm working on and what I'm doing on the vehicle. So a lot of times directions are made for the lowest common denominator. They're really written for someone who might not be as familiar with the system as they should be. And we want to put everything in there to keep them as safe as possible and not damage themselves or the vehicle. And on the other hand, if I am able to look at something and know how it works and know there's no voltage there, there can't be any voltage there, why do I need to wear a glove there just because the instructions tell me to do so? So that is,
Yeah, no, I got it.
that's kind of the
Understood.
evolution of knowledge, isn't it? When we're 5, we're probably told never touch the stove. When it's dinner time, someone's probably asking you to touch the stove because they don't want to cook.
Yeah, no, I've come to the conclusion, well, with my particular, I'm not sure if every car is like that, but every time I disconnect the negative terminal or to work on whatever, or I noticed that I have to go through a couple drive cycles to set my readiness monitors.
Correct. And all cars are like that. And some cars, the windows don't go up and down right. The sunroof doesn't work. You lose all your radio memories. You might have to put a code in the radio. The car might stall or might not stay running. There's a plethora of things that can go wrong, especially on a Friday afternoon, disconnecting a negative battery cable. And if it's a Friday afternoon before a holiday weekend, guaranteed something will go wrong. So high voltage battery, 3 major stages of development. First generation hybrid electric drives, which were normally an assist system, so they were a lower voltage. True high voltage electric drive line, where we use a nominal voltage of 300 volts, although reality we're slightly above or below that. And then we moved into lithium ion batteries is where we currently are. As I mentioned earlier, Toyota is doing stuff with solid state batteries where they're not using lithium. And a couple reasons for that is the stability issues with lithium. Also, lithium is very hard to get, not only from an expense standpoint, but the countries that lithium is in is China and developing countries in Africa. So there's a lot of ethical issues with getting lithium, and they're not sure if there is enough lithium to propel us into the future. So they're actually looking at a nickel battery with a small amount of aluminum in it and stuff like that, and a solid state battery without either a liquid or paste electrolyte. And they're also looking, they have better battery storage capacity, more energy can be stored, and a greater lifespan. So it looks like that's where we're going, but currently no one has put them in a vehicle yet. And that's why they're not on my list yet of things you're going to see. Dual voltage system, 12 volts for conventional electronic circuits. So my internal combustion engine, or ICE as we call it in hybrid terms, is still going to work on 12 volts. All my windows, not so much air conditioning, my air conditioning controls, my blower motor, my lights is also 12 volts. And then I have a high voltage system for my AC compressor on most hybrid vehicles. Some early ones did not do that. My motor generator, my inverter, and my high voltage battery. My high voltage battery is normally mounted in the chassis, often behind or under the rear seats or in the trunk area. So it's pretty central. A lot of cars put it between the driver and passenger seat down that center arm, and then underneath or right behind the rear seat. It's not going to be in the full trunk area because in case of collision, we don't want it crushed. So it's going to be maybe between the rear strut towers forward. Larger full size or full electric vehicles could be equipped with 2 or 3 batteries. So here is a high voltage battery. This happens to be from Toyota, made up of many small battery cells inside several battery packs, wired in series, producing a high voltage and current. High voltage battery cell is an individual rechargeable battery. So battery cells, each cell in a nickel metal hydride battery, which this is 1.2 volts. Each cell in a lithium ion battery is 3.6 volts. So all we're doing is stacking all these together to get that 2, 3, 400 volt battery. So here is a couple examples of the design we've used for nickel metal hydride. On the left looks like a bunch of D-cell batteries shrink wrapped together. This style is used by Honda and some Ford products. This other style is a flat cell. This was used by Toyota and many other manufacturers. And these are wired, just like I showed you with the small batteries yesterday, where we're going to go from positive to negative to positive to negative until I get the amount of volts I want. Just like we did with these two 1.5 volt batteries, I now have a 3 volt battery. And we're doing this and doing this and doing this till we have hundreds of battery cells.
How long would the cells last usually if it's lithium ion?
You know, the manufacturers will have to warranty them for 10 years. The issue we see with hybrid vehicles, electric vehicles, is after that first battery goes bad, there is generally not a new replacement battery available, only a rebuilt battery available for it. And the rebuilt batteries tend to last 3 years, 4 years. So the issue we have really with, we see with a lot of hybrid vehicles and electric vehicles is their resale value is horrible. Take a Nissan Leaf, for example. You know, you can get a Nissan Leaf pretty cheap. It's all electric, but as the battery ages, its range gets shorter and shorter. So now I have a Nissan Leaf, the battery's bad. I've only been able to go 40 miles on a charge, the same charge that used to get me 80 miles, 90 miles. So now I want to put a new battery in my Leaf. The battery itself is over $7,000. Then I got to pay someone to take the whole bottom of the vehicle off to put the new battery in. The Nissan Leaf itself only sells used for $4,000. So what do you think happens with these cars? They get what? Scrapped. So you have a car now, you figure the average age of the fleet currently is about 12 years. And what I mean by the fleet, that's all the vehicles registered on the road. The average is 12 years. Some of these electric vehicles and even hybrid vehicles, because the batteries are so expensive, end up being retired before that 12-year mark. And so you see where if you're talking about, you know, the total carbon footprint or the total impact on the environment, or the total energy consumed to manufacture and build a car and fuel a car to go from point A to point B, I think we need to look at that end of life. And then how do we get rid of, what do we do with the lithium ion batteries? Because currently they're not recycling them. So is that new hazardous waste we're making? So there's a lot of things as we rush into this technology that sometimes we don't look at the whole picture. And that's a discussion for a different day. But it is, again, like I always tell you, the purpose of this class is to ask questions. One of the discussion posts I saw was about, you know, an electric vehicle, you know, being cleaner for the environment. And certainly that can be true if I'm looking at my carbon footprint going from point A to point B. But I think what we need to do is step back and think, how was that electricity generated? What I can tell you is if the electricity is generated by coal, I have a lower carbon footprint driving my 4-cylinder Camry that's not a hybrid than driving a full electric vehicle or hybrid electric vehicle if that electricity is generated by coal, which it is in the majority of the country. So you can see, you know, sometimes we don't take it that step further to go, yeah, the electricity is treated, but how are we making the electricity? Where is that coming from? How long do the batteries last? So that was a great question. How long do they last? How do we get rid of them when we're done? What are we doing with them? Those are all great questions. In this class, I really try to concentrate more on how it's built and the technology, but I certainly encourage you to find answers to those questions. And that's why we do things like the discussion board. That's why we have these conversations in class, is to bring those questions up because they're great questions.
Mr. Brian,
yeah,
as long as we're talking about this and power systems, where do fuel cells from hydrogen come into the play?
Okay, great question. So a hydrogen fuel cell is a device that converts hydrogen into electricity, for those of you who aren't familiar with it. And there are a couple of hydrogen fuel cell vehicles sold here in California, both one by Honda and one by Toyota. There is a hydrogen fueling station in Sorrento Valley off Carmel Valley Road. They're supposed to be putting another one in Mission Valley. I don't know if it got installed or not with the COVID thing. I haven't checked. The hydrogen fuel cell vehicles have a lifespan of 15 years currently, because the high pressure tank that the hydrogen goes into is only certified for 15 years from date of manufacture. It cannot be filled after that. And there's software to prevent that. I'm not saying people won't figure out a way around the software and illegally fill vehicles. I'm not dumb, that'll happen. But we're talking about the technology. Personally, I really like hydrogen fuel cell technology. You have no range anxiety. Your refill time is the same as it is for gasoline. It's extremely clean depending on how we generate the hydrogen. You're using hydrogen to generate electricity. So you're using the same electric motors that we use in plug-in electric vehicles or in hybrid vehicles that we're talking about here. And the advantage of electric motors is we can use those on big trucks. We can use those on semis because you have 100% of the motor's available torque at 1 RPM. I don't need to rev the engine up to start getting power. And with hydrogen fuel cell technology, we have the opportunity to really do some stuff. So 10 years ago, 11 years ago now, the state of California, California Resources Board, felt that hydrogen was the future. And by 2040, they expected all vehicles to be sold in California to either be plug-in electric vehicles or hydrogen fuel cell vehicles. That is the memorandum as far as in legislation, what they're trying to do and what they expect to do. Now, 2040 is 19 years away. A lot of technology can happen between now and then, and this was done 10 years ago. But it gives you an idea of where the push is and where that technology is being driven. So they've done one of the issues we have with hydrogen fuel cells is that if the air freezes or the fuel cell freezes, it gets damaged and won't work. Well, they now have hydrogen fuel cells that'll operate down to temperatures as low as 20 below zero and not freeze the water in the air. So they're doing some really cool stuff. It's not all the way there yet. The infrastructure for hydrogen isn't there, but I do think that the hydrogen has better long-term potential than straight electric, especially if you consider driving coast to coast, trucks, things like that. It's easier to transport that hydrogen, and we can generate hydrogen from garbage. So we have avenues to generate hydrogen in ways that are currently just emitting methane gas into the atmosphere. So there's some extremely clean ways to generate hydrogen, although it takes a great deal of energy to generate hydrogen. So it is fascinating. I've been following this technology for over 10 years. I've read a lot of papers on it, read a lot of research on it, a lot of documentation. And I would encourage you to do the same and make up your own mind and see what you think about where we're going and the technology. And from a person who worked on cars and a person who trains people that want to work on cars, I look to the future because I want to see what are you going to need to know in 5 years. So a lot of this class is not about how to fix the cars that were built 10 years ago, 20 years ago, or 30 years ago. It's how do you build the cars that are made this year? How are you going to fix the cars that are made in 5 years? How are you going to fix the cars that are made in 10 or 20 years? Those are the keys, and we only get there by learning how to ask questions. So hopefully I answered what I thought of hydrogen fuel cell okay.
Well, so with everything you've said, including the fact that I understand the hydrogen system is much lighter than a battery system, so you gain some there. And with companies like Nikola trying to put hydrogen refueling stations across the country, why is it that electric vehicles are much more popular than hydrogen fuel cell vehicles?
Okay, a couple points there. First of all, hydrogen fuel cell vehicles still have a battery. They're going to have a battery more comparable with what we see in a hybrid vehicle today. because a hydrogen fuel cell vehicle is a hybrid vehicle. Okay, so the only difference is instead of having an internal combustion engine, we have a fuel cell. So, you know, even Mari, Toyota markets their Mari as a hybrid vehicle. So it is a hybrid. So the transmission drive line and the battery setup is the same, whether on a hybrid or a hydrogen fuel cell vehicle. So the difference is the weight of the tank and the space the tank takes up and the weight of the actual fuel cell. So, and they're comparable to what an internal combustion engine weighs. And weight is not as big a deal on an electric vehicle or a hydrogen vehicle or a hybrid vehicle as it is on a gasoline or diesel powered vehicle. Because even though it takes more energy to get that vehicle going, I recoup that energy using regeneration stopping. So it actually benefits them to have a little bit of weight. So that doesn't hurt them. I think the big reason why, two big reasons why we see a lot of resistance to hydrogen fuel technology is one is they equate hydrogen with the Hindenburg. They equate hydrogen with we're going to blow up, burn to death, and die. Very similar to how people equated AC electricity 100+ years ago to AC was deadly and DC was safe. So I think there's a certain consumer image and fear of hydrogen that has prevented some of that. The other thing is our infrastructure for hydrogen, once you get out of the LA basin and once you get out of San Francisco, is not sufficient. And until there's enough infrastructure, you're not going to see it grow. Plus, if you buy a hydrogen vehicle from Toyota, you have to sign that you will not take it out of the state of California. So it's a California only car. It's a limited market release. And part of that's due to infrastructure. Part of that's due to climate. There's a couple different issues that they're still addressing there. And part of it is they want to be able to service that vehicle if it breaks down. The dealers outside of California aren't ready to do that. So Toyota is looking to grow that throughout the country and expand that. But that was some of the early limitations we saw in it. But I hear a lot, and I see it on different blogs or things. People really associate hydrogen with I'm going to die in a ball of fire if I get in an accident. And that's just not true.
Or the humanity.
Yes, exactly. And so that is really, I think, where where a lot of the issue is. They did play with hydrogen on internal combustion engines, but they couldn't get the emissions low enough to meet standards because of that. I'll get into a little bit about more of that when we talk about fuel and stoichiometry, about why we can't burn hydrogen in an internal combustion engine. It's not that it doesn't work, it's just that it's not clean.
Thank you.
You bet. So one of the questions I have here is what do disconnects do? So you saw that Toyota disconnect. I got to have my gloves on to pull out. Here is the disconnect on the schematic right here. And here's the disconnect right here where it's attached to my battery. So you see all these battery cell packs. And then you see the disconnects connected here and here. Well, this is in the middle of basically a big battery. So if I have a bunch of battery cells put together and they're connected end to end, here to here to here, what's the difference in voltage between this end and this end? If I take a voltmeter, what's that going to read? Is there resistance between these two pieces?
No.
It's a connection, right? So if it's a connection, it has to be what? Electrically the same. If it's electrically the same, what's the difference in voltage between the two sides? Zero.
Zero.
That's why there's no voltage here, because it's in the middle of a series circuit. And we know Ohm's law says that in order to have a voltage differential, I have to have current flow and I have to have what? Resistance. And there's no resistance between those 2 points. Therefore, there can't be any voltage. Knowledge is a powerful thing, isn't it? Now, again, some manufacturers put their disconnect at the end where it has all 300 volts of the disconnect. You want to wear gloves. Other manufacturers put it like Toyota does, right in the middle where there's no voltage there. That's why some you need to wear gloves and some you don't. If you're not sure, the directions always say put on gloves. So here's an individual battery cell pack. And we can see 6 cells here, 1, 2, 3, 4, 5, 6. Each cell has 1.2 volts. So that's very different than my lead acid. You remember voltage comes from chemistry. So my lead acid chemistry and my 12 volt battery generates 2.1 volts per cell, where my nickel metal hydride technology here only generates 1.2 volts per cell. Remember, so my voltage is limited by the chemistry. So here I have 6 battery cells in series. So if I go between my positive post and my negative post, I'm going to have 7.2 volts on a fully charged battery. Here is a Honda battery with the same technology, nickel metal hydride, but these are round, each in 6 cell packs, so 7.2 volts each. And these are all stacked in series to make, this is like a 142 volt battery when it's built. So nickel metal hydride cell generates about 1.2 to 1.6 volts DC. Depending on its state of charge, its static voltage is 1.2 volts. Individually sealed and holds semi-solid electrolyte, acid, paste, or gel around positive and negative plates. Soldered or mechanically fastened to adjacent cells. So a hybrid battery with nickel metal hydride normally consists of how many cells in each of those little battery blocks?
6.
6. Yep.
Number 3.
Number 3. I could reword that question a little better, is why I helped you so much with it. So a set of low voltage battery cells in series, a high voltage battery has 30 to 40 individual battery packs, even more for all electric vehicles. So we're taking that 7.2 volts. If I have 2 of those, I have 14.4, 4 of those 28.8, and then do the math. So I can get up, 40 of them, I get what, 288 volts. So I just add that up and add that up using my series circuit rule, and what, I can get the voltage that I want as an engineer. Now, these cells, remember we talked about cycling rate. So these batteries, we never want them to go completely dead, and we never want them to get completely full. So a nickel metal hydride battery, if I'm looking at the dash and it says it's 100% charged, that's normally about a 60% state of charge. If it says it's only 20% charged or empty, that's normally only a 40% state of charge. So the battery cycles between 40 and 60% normally. That's where they're made to cycle at. And that's why they're not ideal for plug-in electric vehicles. So lithium ion batteries are used mostly for plug-ins. They have larger capacity, not higher voltage. So they use the same voltage. So even though the cells each have 3.6 volts, the batteries overall are in the same voltage range, but they have more capacity. They also have the ability with the lithium ion to not remember their state of charge. So they're able to be charged up to about 99% and discharged down to between 20 and 30%. So they have a much bigger cycle range, which makes them ideal for a plug-in electric vehicle, because it's going to give me more range with a lithium ion battery, because I can start higher and I still have power at a lower level. If I'm using nickel metal hydride, that's a pretty narrow window, and I'm going to go through that pretty quickly. So they don't work real well for plug-in electrics or full electric vehicles. And that's why lithium ion was such a big jump. That's why that was so instrumental in the develop of our full electric vehicles, was this lithium ion technology. The issue with it is lithium ion doesn't like heat. So a lot of these systems, actually all battery systems, have some sort of battery cooling. A lot of these lithium ion systems actually have liquid cooling systems or refrigerant cooling systems to maintain battery temperature. And we brought up a couple of days ago about battery temperature sensors. All high voltage batteries have at least one temperature sensor, and many of them have 3, 4, or 5 temperature sensors, because they really want to monitor how this is working. And so this is from a Chevy Volt, and you can see this is a huge battery setup, actually 3 different sections connected together. Right here, these bolt holes are where it connects to the bottom of the vehicle. So this actually drops out of the vehicle from the bottom, which is very common. And Jaguar does this, a lot of manufacturers do this. So they have special lifts and special adapters for taking these batteries out the bottom of the vehicle. And these are extremely heavy. So you disconnect some electrical connectors and then you drop the whole thing out the bottom of the vehicle. So we think about replacing an engine today. Here we're replacing a battery assembly. About the same money. So here, one of the advantages we have with hybrid vehicles is we normally have really, really good data in the scan tool. So in this case, off a Chevy Volt, we have 96 different battery cell groups. And I can see the voltage for each one of those. And it's going to set a code if one isn't like the others outside of a certain percentage. So you can see the testing that we did on a regular 12-volt battery, whether it's hydrometer test, whether it's a carbon pile load test, any of those things, I'm not going to do here. I'm going to rely on my computer to watch the data, and it's going to set a code if the data doesn't look correct. From there, I can graph this data or look at this data and verify the fault. So in this case, 96 batteries at 3.86 per cell, but there's a total of 288 batteries. So what they did here is a little different. They took 3 lithium-ion batteries and wired them in parallel, and then took each set of 3 and wired those in series. So that gave it a lot more amperage capacity since this is a plug-in electric vehicle, which gives it a lot better range. So different manufacturers will design their batteries slightly differently, doing the same thing, but they put them together a little different using our series parallel rules, rules and our parallel circuit rules. So it's interesting how they build these, but understanding what we learned last week in basic electricity about series or parallel allows us for these batteries that are pretty complicated to really make sense and allows them to diagnose them with a scan tool. So battery pack voltage, nickel metal hydride, 7.2 to 8.2 volts, depending on a pack. Battery pack voltage on lithium ion, because they're parallel, even though there's 3.6 volt cells there, but they're wired in parallel. So the voltage doesn't change, just the amperage or the current potential changes. Banks of batteries are wired in series to produce anywhere from 100 to 300 volts DC. As I mentioned, some of these belt alternator assist systems are down as low as 42 to 48 volts, but we don't consider them a true hybrid, and that's why I didn't include them here. Battery packs also have fuses to protect against shorts or excessive current draw from each group of cells. The batteries have their own computer. So cars today have a lot of computers. So I have a computer to run my engine, my internal combustion engine, oftentimes a powertrain control module. And then I'm going to have 1 or 2 batteries for my hybrid system. I might have one battery that includes the battery management, or my battery might get its own special computer. And then there's another computer that controls the inverter, the charging, and the hybrid management system. So we can quickly start adding up computers here, and each computer has a dedicated task. So high voltage battery temperature sensors protect against battery thermal and overheating damage. So if my cooling fan stops working or my cooling system for the battery stops working and the battery starts getting hot, we're going to reduce power. If it's a plug-in electric, we may shut the car off altogether. If it's a hybrid, we might keep it running on the gasoline engine and not let it run on electric. We might stop charging the battery. We're going to set codes. We're going to turn the light on, telling you it's time to go get this serviced and diagnosed. High voltage battery cables are large plastic conductors coated with bright orange plastic insulation. Anything over 60 volts by regulation has to be orange. They are able to put 42 volt systems in orange if they want. They're not required to. But if I see orange wires or orange cables, that should be a warning to me. I don't want to stick that with a power probe or a test light. I don't want to put my hands on it. I don't want to wash it with soap and water because it's dirty. That's high voltage. That's danger. So I have AC cables. I also have high voltage battery cables that connect the high voltage DC electricity to my high voltage power control module or inverter. And then I have high voltage motor generator cables. These are going to be 3-phase AC cables for power control to the module and to the motor generator. So as I look here, I can see 2 different sets of battery cables. You see at the bottom here, there's 3 cables. That means it's 3-phase and it's AC electricity. So that's going to be going, these are pretty small, so they're probably going to an air conditioning compressor. If they're bigger, they might be going to one of my motor generators in the transmission. And these two big cables here go between my inverter and my battery. So these are DC current. So we can see the DC current comes in. This is my inverter that converts AC to DC and DC to AC. It also converts to sine wave and tells my charging system, do I want to charge the battery, or do I want to use the battery to make the vehicle go forward? So it controls the phase current. Do I want to use my motor generator as a motor, or do I want to use it as a generator? And that's going to be largely based on condition of the battery and driver intent. Is your foot put to the floor? Obviously, we want to use that as a motor because we want to make the car go fast. Is your foot off the pedal? Then I could probably use it as a generator to put some energy back in the battery. So one of the things we do with high voltage systems is we want to look at the batteries and see if one looks different. And this happens to be a Toyota Prius, and it has 14 different battery blocks. Each battery block has 2 cell packs. So its nominal voltage would be 14.4 volts. And then the charging system or the high voltage system is going to elevate that up. And we don't normally set codes if everyone's low or everyone's high. We can set a code if everyone's too low. We won't let the car start under 20% state of charge. But most of our codes, or most of the codes that say the battery's bad, is because one doesn't look like the other. So it's real helpful to graph data, because then I can look at what happens over time to see if one doesn't look like the other. So I can't make a jack-in-the-box jumbo jack. I can eat them real good, but I can't make them. But if you give me 2 of them and take something out of one, I could probably tell you what's missing. And I think most of us can do that. So as I look at this picture, I'm looking at all my different battery blocks here. And so I have 14 blocks, and then I have right here is my engine speed. So my engine speed is going to look different because it's not a battery block. If I look at the numbers on the side, this is the minimum voltage and highest voltage in that block while I did this test. And what I'm looking for is either a pattern that looks different, or the numbers here look extremely different. And is there any cell here that looks different than all the others?
Yeah. Look, number 7.
Can you tell what number it is, or you want to tell me where to move my cursor?
124892.
Is the the block number 7.
Number 7 right here?
Yeah.
You're right, number 7. So let's look at number 7. Does my picture look different? Everyone else comes out and has a nice sharp drop and comes over. This one slopes, doesn't it? So you can kind of see the power of graphing right here. Without even knowing what you're looking for, I can see something looks different. It gets my attention. Imagine looking at all these 14 or 15 numbers in a row, trying to see which one does something different. We wouldn't see it, but graphing it, boy, it just sticks out. And then I can also look at my numbers. My lowest voltage is 15.61 volts. Anyone else even under 16? Oh, there's 16. No one else is even under 16, and only 1 or 2 are under 17. So it went way lower. How about anyone else go over 18? No one else went over 18 volts. So it went much higher. So, and that's indicative of a bad battery. A bad battery will charge more quickly and decharge more quickly than a healthy battery. And so this particular car had a code for replace battery. Now, instead of just replacing the battery, we want to verify the failure because other things can set that code. And so what we did a quick test, a quick graphing of the test. This test took only a couple minutes, and we could quickly see exactly why that code set. It has a bad block. Now, Toyota says replace the whole battery. If a lot of the guys that use the taxi cabs go in and they just replace that one battery block and they drive the car for a few more months. I wouldn't do that to a customer's car, but that would get the car running. Again, the idea is for everyone to be even. So this is how we would die. Very, very different than our carbon pile tester or Medtronics, isn't it?
So, Mr. Robert, you're saying that if there's only one bad block, you have to replace the whole battery?
That is what the manufacturers recommend. And the reason for that is because they want them all to be the same. If all this battery, say it's 10 years old, if I just put in one new block, that new block isn't going to be new. It's going to be used out of a junkyard. How good is that? Is it equally bad or good as all the other blocks? So I could put a new 2-cell pack in a block and still get the same code because it might be much better than everybody else. So Toyotas are pretty forgiving. A lot of times you can get away with it on Toyota. Other manufacturers are much more stringent and you won't. But Toyota doesn't recommend doing that. And again, even if it's a customer, if I put a whole new battery in for you, parts and labor, we're probably talking $2,200-$2,300. I can give you a couple-year warranty, and your car is probably going to be good because I can still get a new Toyota one. You're probably not going to have battery problems for the next 7 to 12 years. Or I can go in and put in just the battery block that's bad. Hope it works. It probably will be in a Toyota. And you may have one of these other blocks that did go down below 17 volts. I mean, yeah, go down below 17, act up next week or next month or in 3 months. So, and then you're going to pay me to diagnose it again, take the battery out and take it apart again, which is a couple $100, and then put it back together and wait for the next one to go bad. So you can see where, it's the old time versus money thing. Customers, when they come into the shop, they're paying money to get what? Reliability. They don't want to be stuck somewhere at 10 o'clock at night. They don't want to miss a day of work because they can't get in there because their car doesn't start or doesn't get there. And if they do, they're going to be really mad at me as the person who fixed the car. On the other hand, if someone's working on their own car or helping out a friend or family member and knows the upsides or downsides, now they're making an informed decision for what's right for them. And for example, a taxi cab, they put 400,000 or 500,000 miles on these taxi cabs. They run them into the ground. They're just replacing the block, driving another month or two, and then replacing the next block that goes bad. They're just putting out fires. They're not investing, an expensive battery, an $1,800 battery, into their taxi cab that has 300,000 miles that's been salvaged twice. They're just fixing what's wrong and getting a few more miles out of it. And there's nothing wrong with that business model because that's what they've decided works. The thing is, I wouldn't do that to a customer's car because I don't want them mad at me that they missed their kid's graduation or they didn't get to work and got fired or any of these other things because we cut a corner for them. And and the other thing that we have to look at in California is what's called acceptable trade standards or industry standards. So any repairs I do on a car have to follow industry standards. And that's defined as either the manufacturer's procedures or following the procedures in a nationally recognized trade publication. So that can be a magazine, that could be Mitchell, that could be All Data, that could be any of those things. As long as I follow those procedures, I'm okay. None of those say it's okay to replace just one battery block. So if I'm doing it, I'm actually violating acceptable trade standards or industry standards for the automotive industry. So if my customer complains, even if they agreed to it and said that's what they want, 3 months later, 4 months later, 6 months later, they complain about it and they complain to the Bureau, I'm going to get cited and have to refund all the money.
Can you have your customer sign like some sort of a waiver because stating that that's what they want you to do? So you won't be responsible?
No, because I'm the professional. So you can't sign away that you want me to do something that violates trade standards. You can't sign that away. So you can sign that and hey, we're all good. But if you turn around later and sue me or file a complaint, that's not worth the paper it's written on. Because all the customer does is, well, I didn't understand, or I thought it'd be better, or he told me to sign this, I didn't understand. It doesn't mean anything.
Oh, really? Because
Yep.
I remember when we had our car fixed for something, they asked us to sign something because we refused to have it fixed or repaired or whatever. I forgot. So that doesn't mean a thing that we signed for it, and if something happened?
No, not really. You know, might have you sign something, say that they recommended that you do these things and sign here that I discussed it with you. That's an internal bookkeeping thing. And that might be that if that problem happens in the future, they can say, no, we did tell the customer about it. That signature would be valid because they're not asking you to sign something that changes or violates what the law is or what the administrative code is. When you ask someone to sign, yeah, I'm not allowed to do this, but just sign here that you want me to do this, that you want me to put your car back on the road that's unsafe. So for example, I'll go back to tires. You guys, a lot of you just finished the brake and suspension class. And I'm sure you learned about the case of against Massey Ford regarding tires and why we no longer plug tires in the state of California. Did you guys learn about that case in the class?
No.
Don't remember it being specifically that, but I think I remember learning that we're not allowed to plug tires anymore.
Okay, so I plugged tires for years. And I still will on my own stuff.
Now, what's plugging a tire?
Plugging a tire is where you remove the nail or screw and you use a self-vulcanizing plug to go back into the hole that seals the tire and prevents it from leaking.
So
And
that's different than patch?
What's that?
That's different than patching it?
That's different than patching it. Patching it is where you just go on the inside of the tire, break it down and put a patch in, but you don't seal where the hole is going through the cord body or through the rubber of the tire, and water gets in there and actually causes the tire to separate. So in California, we're not allowed to patch and we're not allowed to plug. We have to use a combination of a patch and a plug because the industry decided, American Tire Rubber Manufacturers Association decided that was the best way to do it. And there was a case here in San Diego County at Massey Ford where someone brought their van in and the tire needed to be repaired. And the tire was pretty worn out. And it said, you know what, can you just repair it to get me back on the road and I'll replace my tire next week. And so they signed that they knew their tire needed to be replaced and Massey Ford plugged the tire for them. 6 to 8 months later, I don't remember the exact timing, they were driving through Arizona. That tire blew out. The van flipped over and both occupants were killed, leaving 4 orphans. The dealership was sued because they violated industry practices by plugging the tire that should not have been installed on the vehicle. Even though the customer signed, even though the customer said that they were going to replace the following week. And that tire was repaired improperly because it was plugged and that didn't follow their guidelines either. Now, keep in mind, the plug is not what caused the tire to wear out. It failed at a different point and forensics proved that. Massey was held liable and paid over $20 million because they acknowledged by the customer signing that the tire should not be put on, putting the tire on the car and repairing a tire that should not have been repaired. And that is why we no longer plug tires. So that happened in the judicial side, I think it was 2011. Just last year or within the last 2 years, the state legislature just passed a law saying it's not legal to plug a tire. Before then, it was the courts that had decided that you couldn't do it in California, and the industry reacted because of the amount of dollars in the lawsuit. Just within the last 2 years, it became actual law in the regulations. But going back to the question that Connie had, can't the customer just sign? No. And this is a great example of that. The customer signed, said, hey, this is what I want. But yet when things go wrong, the shop is the professional. They know better. The customer can't sign away something that by statute, they're considered not to fully understand. The shop is the professional. The shop fully understands the customer is considered uninformed of the complete consequences, and therefore they can't sign that away. Did I answer the question okay for you, Connie?
Yes, sir. So in cases like that, since you said it's legislatively not correct to repair something that's, illegal, so
Right.
you just send them away?
Yeah, you just let the customer know, I can't install that on the car, or I can't do that. Do you have a spare? I can sell your tire. We can put a spare on. We do the options, but I can't do that. And working service stations for a number of years, I used to do that a lot. We'd have customers come in all the time wanting tires repaired that exceeded the limits that we were allowed to repair tires and following industry practices. And we told customers we can't repair it. And they might end up going somewhere else and getting repaired. They come back, yell at us, call us crooks, all kinds of stuff. When there's other people around, of course, service station, there's always people around. So I've taken a fair amount of abuse over the years for things like that, for holding the line on what is right and what's wrong. But at the end of the day, I still sleep at night, and I'm not putting anyone's life at risk. So
Yeah, I've seen a lot of used tire shops. They still do plugging.
right. So I just try to do the right thing. I think that's all any of us can do. And if someone finds someone to do the wrong thing, that's on them.
Why do they still sell these repair kits with plug-in?
Well, they sell them at the auto parts store, right? Because who's buying them? Is the shop buying them, or is the consumer buying them?
Okay.
The
Consumer.
consumer's buying them, right? So those rules don't go to the consumer, just like with air conditioning. If I'm going to service air conditioning in a shop, I have to have a recovery machine. I have to be certified. But yet you can go into XYZ Auto Parts store and buy a can of refrigerant without a license, without anything, and it can go right in the atmosphere. But I have to have thousands of dollars of equipment and be certified before I can charge a customer or do air conditioning service. So there's a lot of rules that are on industry that are not on individuals, right or wrong. We can argue that. But that's why in this class, when I talk about repairing things like high voltage batteries, I break down between this is what we do in industry. This is the correct way of doing it. And yes, I understand that people do it differently when it's their own car, when it's their own vehicle, or I understand there's different people that might work outside those standards. So there's a difference between what I can technically do and what I should morally do and what I should legally do. And so when we get into these discussions, I really try to separate that to give you the best education I can.
So
Yeah,
Brian,
sorry.
Yes.
so you're saying, just to be clear, so a patch is illegal, but like unless it's a patch with a plug?
Yeah,
Or
it
like
has to have the patch, and plug combination. And then you're
Okay.
limited on the angle you can put it through. You have to reseal the inner liner of the tire. There's a whole procedure. They'll come out and do the training at the shop for free. If you,
I was just-
you buy the kit from them, and the kit, the best price I found on the complete kit was O'Reilly, and that's the one we got at the school, which is the complete kit. They make a partial kit, and it doesn't have all the trick tools in it. But the complete kit, that's what we got at the shop. We do a lot of tire repairs at the shop. I mean, you could do a lot of things, but I think knowledge is important, so you do it correctly.
Yeah,
And,
I
and
was just,
again, go ahead.
I was gonna say, I was just curious because I know Discount Tire do it for free, and they do the patch and the plug.
Right.
I just did it on my van a couple weeks ago, and but yeah, I was just like curious. I know if it is too close to the wall, it's not safe, but I didn't know like it has to be so bold to make it legal.
Yeah, exactly. And Discount Tire does do it because they know a lot of them aren't repairable. And guess what? They sell tires. So it's a good, it's good advertising for them. It's a smart business model, I mean, so can't fault them for it. We charge for tire repairs. We've done a lot of tire repairs. But again, it just comes down to what the industry does and what's acceptable. Real quick, I'm going to stop the share. I know we're done, but let me see if I can pull up those gloves real quick I was asked about. And let me pull up that PowerPoint.
Story and
On
last
the negative battery cable, Mr. Brian, when you disconnect the negative battery cable, it's tricking the ECU, right?
Yes,
That you're
disconnect
putting-
the ECU, right? It disconnects everybody.
No, I mean, it's tricking the ECU that you put something in brand new.
Right. Well, it's not tricking the ECU so much that I put something in brand new. What it's doing is it is erasing what's called the keep alive memory in the ECU. It's an adaptation. It's like getting hit on your head and you no longer know how to put your shoes on. So you have to relearn so there's certain things that are base programming. So maybe you know how to walk, maybe you know how to put shoes on, but you don't know how to read. Or you know how to read, but you don't remember what you've read, right? So it's, so there's some base programming in there, and then there's other things that it has to relearn. Kind of like getting amnesia. And let me pull this up. Come on, load. It's a big PowerPoint. It's like 400 meg, so it took a second. All right, let's see.
As long as we're waiting, can we go back to parasitic draw for a moment?
Yes.
So if I wanted to test to find the parasitic draw, and I disconnect the battery and I install my amp meter as part of my voltmeter in series, and then I plug my battery back in. By plugging my battery back in or reconnecting the battery, am I waking up enough stuff to go over my 10 amp max on my ammeter and then let the factory smoke out?
Great question. And as long as the key is out of the ignition and the doors are all closed, no.
Thank you.
So great question. And that's why we, make sure the doors closed, all that stuff before we do that. So I'm going to pull up, since we were talking about hybrids, here's a couple slides I made. This was for a presentation I made for another company, but since I wrote it, I'll steal it and show it to you guys. Let's see here. So this right here is the gloves. This is the box, and it comes into talking about the shelf life, the size, the classification, in this case, class 0, maximum 1000 volts. And then here is the 3 parts of the glove you guys were asking about that I was explaining. So I have the inner liner. I have the inspection date on the lineman's gloves, and then I have the goat skin gloves that go over them. So does this help kind of visualize the 3 gloves and how we'd wear them? Yes, no?
Yes.
Okay.
Yes.
Sorry, I was mute.
No problem. And one of the things I put in here that I probably put in ours, I made a nice slide of some hybrid tools. So these are insulated tools for high voltage, which allows me to work on systems if they're live or potentially live. And then also we mentioned thermal imager for looking at things. And I do have a nice slide here talking about high voltage batteries. So here's a thermal imager. And this is one of those Toyota batteries. So we have all of our battery blocks, and heat is always concentrated in the center of the battery, and the outside of the battery tends to be cooler. And that's why the cells in the center of the battery tend to go bad first, and the ones on the outside of the battery last longer. Is heat. So this is that thermal imager I was talking about. You can see on the screen, I'm ranging between 78 degrees and 107. Where I'm pointing with the bullseye is 97. The lighter the color, the hotter it is, the darker the color, the cooler it is. So that's the thermal imager I mentioned earlier.
Mr. Brian,
Uh-huh.
does the rotten apple principle apply to these batteries?
Yes, absolutely. Any series circuit is affected by everybody else in the circuit. So the rotten apple principle totally applies. If you don't believe me, take a flashlight and has 3 batteries or 5 batteries or whatever. Take one of the good batteries out and put 1 battery in and see how well the flashlight works. And see how long those other 4 batteries last.
Yeah, I know. I remember they say that if you replace the batteries, you have to replace all of them. But when it gets to be expensive and you're trying to save some money, you only replace 1 or a minimum, right?
Right. So that's a great point. So what we do is we let our pocketbook influence us into bad decisions. We know what the right thing to do is, and then it's like, whoa, that's expensive. What else can I do? I no longer care about right. I care about price. And we all do that. And we do that with different things. I don't care if it's fixing a car or remodeling a house or painting or anything you do, right? You have this, I really like this, then you see how much it is. Well, what else do you have, right?
Yes, we go to option B.
Right. And a lot of times on cars, when it comes down to correctly fixing them, there just is no good option B, or option B is not a good repair. But on the other hand, you know, and I hate to say it, but wait a minute, say you have one of these cars and you are getting ready to sell it anyways, and you know what the car is worth. So your choices are, I could sell the car with the bad battery block. I could put a brand new battery in it, but the brand new battery is going to cost me $3,000. I was only going to sell it for $4,500. Or I put the one block in, maybe sell it for $4,000, a little bit less, to let the customer know, hey, the battery, I just replaced one block. It's new. The battery's working fine. It's a 10-year-old car. I have no idea what the future holds. Right? I mean, so you can use that as an option, you know, but you shouldn't say, hey, I just had the battery rebuilt because you put one block in. That wouldn't be ethical.